I would like to extend my special thanks to independent research dentist Farouk Yanik, who prepared this very important and groundbreaking study. He works at Al-Shab Hospital in Baghdad.
Yes, absolutely. It's a fantastic foundation for what we're talking about today.
Right. Now, to kick things off, I want you, the listener, to just picture something for me right now. Imagine a purple dog ghost flying over a blue moon.
And it's almost instantaneous, right? The
Yeah.
moment those words hang in the air, your brain just like paints the image.
We do it so effortlessly that we honestly take it for granted. I think we tend to confuse the mechanical, physical act of making a sound with the profound reality-bending ability to truly speak.
Oh, completely. Because
Yeah.
if you look at animal communication in the wild,
Like a vervet monkey. Right?
yeah, exactly.
Yeah.
A vervet monkey makes a highly specific alarm call because it spots an eagle. But that sound is completely tethered to the present moment.
It just means danger from above, right this second. Run.
Right. That monkey cannot turn to its troop the next afternoon and say, hey, remember that eagle yesterday? I thought it looked a bit like a cloud.
Yeah, because animal communication is essentially a localized warming system.
Exactly. Whereas human language is infinite world building. What we are really talking about here is how our species transcends time and space.
We use these constructed sounds to navigate deep into our past or project decades into the future and, as with the purple dog ghost, construct infinite alternate realities that have never physically existed.
Wild.
It is. And our mission for this deep dive today is to figure out how our species made that massive leap, like how we transition from limited reactionary warning signals to wielding this boundless creative superpower.
Because when you dig into the research, it becomes very clear that language was not just a cultural habit we picked up around the campfire one day.
Right, it wasn't just a trend.
No, it was actually the result of a massive biological and evolutionary gamble. The emergence of language required a series of genetic mutations that fundamentally altered our physical anatomy and our neural wiring.
Which is crazy to think about.
It is, because from a purely evolutionary standpoint, the bodily adaptations required for complex speech were wildly dangerous. They introduced, incredible vulnerabilities to our daily survival.
Which feels totally counterintuitive. You'd think an upgrade would make us safer. But let's start with the physical hardware.
Okay, yeah.
Because before the brain can even attempt to run complex language software, the body needs the physical equipment to produce the intricate sounds. Like you need the speakers before you can play the music.
Exactly. And the fossil record points us back roughly 600,000 years to Homo erectus. Paleoanthropologists studying this era focus on two highly specific anatomical changes.
Okay.
The first one involves the hyoid bone.
The one in the neck.
Yeah, it's this small U-shaped bone in the neck that is unique because it doesn't articulate with any other bones. It just sort of floats there, suspended by muscles and ligaments.
Right.
Now, in a chimpanzee, the hyoid is quite bulky and is attached to large air sacs, which, is incredibly effective for producing loud, booming, intimidating calls across a jungle canopy.
But when we look at the fossils of Homo erectus, that bone loses the bulk. It becomes refined, unattached to those air sacs, and it looks remarkably like our own.
Right. And the second physical shift is arguably even more critical. It has to do with the shape of the skull base. In most primates, the base of the skull is relatively flat, which naturally keeps the larynx, the voice box position, very high up in the throat.
Which is actually a great survival trait, isn't it?
Oh, fantastic.
Yeah.
It allows a primate to breathe and swallow simultaneously without any real risk of choking.
But our ancestors developed a distinctly curved skull base. And that curve essentially forced the larynx to drop much lower down into the neck. And this is where that evolutionary risk you mentioned comes in, right? Because dropping that larynx meant our ancestors suddenly faced a very real, constant danger of choking on their own food.
Yes, daily lethal risk.
Which is mind-blowing. Nature accepted a daily lethal risk just to create an empty space above the vocal cords.
Exactly. That space of pharynx acts exactly like the hollow wooden body of an acoustic guitar. It became a resonating echo chamber, capable of amplifying and shaping incredibly fine-tuned acoustic frequencies.
So it's the ultimate trade-off. We traded eating safely for the acoustic guitar throat.
Pretty much. Without that dropped larynx, producing the sheer variety of sounds necessary for a complex vocabulary is just physically impossible.
Well, wait, If Homo erectus had this upgraded hardware 600,000 years ago, that raises an immediate question.
Were they actually talking?
Yeah.
Were they sitting around the savannah debating the best way to nap flint? Like, were they speaking in full complex sentences?
Well, the archaeological evidence heavily suggests they were not. They utilized what researchers call a multimodal proto-language. Multimodal proto-language. Meaning what exactly?
You can think of it as a really tight integration of physical gestures
Yeah.
combined with highly specific, context-dependent grunts.
Oh, I see.
So if someone picked up the wrong type of rock to strike a fire, their companion wouldn't just point at it. They would point while simultaneously making a distinct grunt that meant, not that one, use this one.
So it's essentially a highly interactive, slightly noisy game of charades.
Yeah, basically.
But even that level of communication shouldn't be underestimated. Because to coordinate shared goals, you need joint attention. And we know Homo erectus managed to cross oceans to reach places like Indonesia.
Which is no small feat.
Right. You cannot stumble your way across treacherous ocean currents on a raft. You have to chop the wood, bind it, paddle in unison, react to changing tides. I mean, that requires serious teamwork.
It absolutely requires a shared mental focus, which their proto-language provided. But a raft crossing, as impressive as it is, still relies on reacting to the immediate physical environment.
Right. It's still tied to the present.
Exactly. Moving from coordinated grunts to modern language to abstract thought and storytelling required a massive software update in the brain to utilize that new throat anatomy.
And the wild thing is, we didn't even know what that software update was until the 1990s. And it was all because of a tragic medical anomaly involving the KE family in the United Kingdom.
Yes, the KE family case completely revolutionized our understanding of the genetics of speech.
Can you walk us through what happened with them?
Sure. So you have an extended family of about 30 individuals across 3 generations, and roughly half of them suffered from a severe condition called developmental apraxia.
And what does that actually mean in practice?
It means they couldn't coordinate the muscles in their face and mouth to articulate words. Now, they possessed completely normal intelligence.
Oh, wow.
Yeah, their inner monologues were perfectly intact, and they could hear and understand everything around them. But they were physically trapped.
Because to say a simple one-syllable word like blue, your brain has to coordinate, what, like 100 different muscles?
Yeah, cross your lips, tongue, jaw, and throat in exact millisecond sequences. And for the affected family members, that coordination system was fundamentally broken.
So how did they figure out the cause?
When geneticists finally managed to map their DNA, they traced this entire systemic communication collapse down to a single mutated letter on chromosome 7. It was a mutation in the FOXP2 gene.
FOXP2?
Yes. FOXP2 is a transcription factor. It functions much like an orchestral conductor, dictating when, where, and how intensely other genes turn on and off.
Right.
And crucially, it is highly active in the basal ganglia, which is a region deep within the brain responsible for managing fine motor control and sequential learning.
But discovering FOXP2 creates a bit of a logical trap, doesn't it?
How so?
Well, if FOXP2 is this magical language gene, well, practically every mammal has it. Mice have a FOXP2 gene. Chimpanzees have it. So if it's just about having the conductor, why aren't the chimps at the zoo quoting Shakespeare?
Ah, that is the perfect question. And it all comes down to microscopic, almost unbelievable differences. Over the vast timeline of mammalian evolution, the human version of the FOXP2 protein shifted.
Okay.
It differs from the chimpanzee version by exactly 2 amino acids.
Just 2?
Just 2 out of hundreds.
That's the equivalent of changing 2 lines of code in a massive operating system.
Exactly. But those 2 lines changed the entire trajectory of our species.
How? What did they actually do?
They created a monosynaptic connection in the human brain. That is, a super-fast, direct, uninterrupted neural pathway linking the brain's motor cortex directly to our vocal cords.
Oh, I see.
Yeah, because in other primates, vocalization pathways are indirect and heavily routed through the emotional centers of the brain. A chimpanzee typically needs a massive, emotional, trigger-like, intense fear of a predator or extreme excitement over food to vocalize.
So it's an involuntary, instinctual reaction to their environment.
Right.
So if a chimp is terrified, it yells. It's essentially a passenger to its own emotional state.
Precisely. But this monosynaptic connection bypassed those emotional security gates entirely. It gave us voluntary, millisecond, precise control over our voice.
Wow.
We gain the ability to make a sound just for the sake of making it, playing our vocal cords like a piano virtuoso, totally independent of how we were actually feeling.
So we gain the mechanical freedom to produce a rapid-fire stream of highly controlled sound.
Yes. But the puzzle doesn't end there, because the Neanderthal paradox complicates this picture immensely.
Right, because if it's just a matter of having the acoustic guitar throat and the upgraded FOXP2 software, Neanderthals should have been writing novels alongside us.
Exactly. We know from sequencing their ancient DNA that they possess the exact same human variant of the FOXP2 gene.
And we also know about their auditory capabilities, right? Because researchers took CT scans of Neanderthal fossil skulls, I think it was from the Atapuerca cave in Spain, and they reconstructed their inner ear cavities.
Yes. And the fluid dynamics of those reconstructed ears show they were tuned perfectly to pick up frequencies in the 4 to 5 kilohertz range.
Yes. Which is incredibly specific and highly relevant to how we speak today. Because in human speech, vowels are essentially continuous open throat sounds. They carry the raw emotion and the volume.
Right.
But consonants, the hard, sharp sounds like P, T, and K operate right in that 4 to 5 kilohertz frequency range. Consonants are the data.
Exactly. They are the sharp boundaries that slice a continuous stream of sound into distinct, comprehensible words.
So their internal microphones were perfectly tuned to pick up the high-frequency data of speech. They had the physical anatomy, they had the FOXP2 conductor.
And all the pieces.
So why didn't they conquer the globe? Like, what was their missing link?
Well, the conductor was the same, but the sheet music was different. The divergence between us and Neanderthals came down to regulatory genes, specifically non-coding regions of DNA called SMARCO2 enhancers.
SMARCO2 enhancers.
Yeah. These enhancers don't build proteins themselves. They control the volume knobs on how genes like FOXP2 shape the developing brain.
Okay, so they're regulating the expression of the genes.
Right. And in modern humans, those regulatory volume knobs were cranked up, leading to a massive expansion in specific neural architecture. Broca's area, which sits in the frontal lobe and handles syntax, the complex mathematical rules of grammar expanded significantly.
Wow.
And even more importantly, a neural pathway called the arcuate fasciculus thickened massively.
So wait, how does that pathway work?
Think of the brain as having a massive storage center where it keeps all its vocabulary, and a separate construction site, Broca's area, where it actually builds the sentences using grammatical rules.
Okay.
The arcuate fasciculus is the road connecting those two locations.
Oh, I love that analogy. So for Neanderthals, that neural pathway was like a dirt road. They could send words over to the construction site, but the traffic was slow, maybe a few simple concepts at a time.
Right.
But modern humans developed a broadband fiber optic cable. That thick, high-speed neural highway allows us to retrieve a word, apply a complex grammatical rule to it, and send it to the motor cortex to be spoken, all in a fraction of a millisecond.
Exactly. It's the processing speed required to handle nested, complicated sentences, because syntax requires immense computational power.
Yeah.
A dirt road just cannot handle the traffic of a sentence that references the past, conditions the future, and holds multiple subjects at once.
That makes total sense. But looking at the timeline, there's a massive glaring gap here.
The 500,000-year delay.
Yeah. If our physical anatomy was largely ready 600,000 years ago, and our brain architecture was slowly getting wired up with these fiber optic cables, why does the archaeological record look like a ghost town for 500,000 years?
It is a profound mystery, initially.
Because of the great cognitive revolution, when we suddenly see delicate bone needles for sewing tailored clothes, bows and arrows, and incredible abstract art like the Lion Man statue in Germany, that all explodes onto the scene only about 100,000 years ago.
Right. It is a 500,000-year delay between having the capacity for complex thought and actually executing it. And the key to that explosion lies in a radical evolutionary mutation that caused prefrontal cortex delay, or PFC delay.
Let's examine what that means for a growing brain, because from a survival standpoint, it sounds like an absolute nightmare.
It really does.
Like, when a chimpanzee is born, its brain matures and hardens very rapidly. Within a few months, a process called neural pruning takes place. The brain cuts away unused connections, locking in its essential pathways. It becomes rigid, efficient, and ready to survive in a hostile jungle.
But in humans, the PFC delay mutation kicked in. Our prefrontal cortex, the center for logic, planning, and complex social behavior, stays soft, unpruned, and chaotic for 10 to 15 years.
We basically left our central operating system in a highly vulnerable developer mode with all the firewalls down for a decade.
That's a great way to put it.
I mean, a 3-year-old chimp knows exactly how to step away from a steep cliff edge. A 3-year-old human will happily walk right off that same cliff because they are distracted by a shiny rock.
Exactly.
Leaving your offspring completely helpless and foolish for a decade in a world filled with apex predators is a massive evolutionary risk.
It is. But nature only selects for that kind of profound vulnerability if the reward is unparalleled. And the reward was neuroplasticity. Language syntax, the intricate grammar that organizes our thoughts, is essentially invisible math.
Yeah.
You cannot learn it with a rigid, hardened brain that is solely focused on immediate survival.
Right.
The extended childhood provided by PFC delay allowed the human brain to act like a sponge. It gave the critical window of time needed to absorb environmental inputs and physically rewire itself to process infinite linguistic rules.
Okay, so we needed this long, slow, dangerous childhood to wire the fiber optic cables properly, but that introduces a massive chicken and egg paradox.
Who spoke it first?
Exactly. If our long childhood allowed us to absorb and learn complex syntax, who was speaking it first? There was no established language for those very first slow-developing kids to copy. You can't absorb complex grammar from parents who are still just pointing at rocks and grunting.
Right. That paradox is the crux of the linguistic leap, and it brings us to the Romulus and Remus hypothesis.
Romulus and Remus.
Yes. It's a highly compelling theory in evolutionary linguistics named after the mythical twin founders of Rome.
The idea being that the founders built an empire from scratch?
Precisely the concept. The hypothesis suggests that while the adults were locked into using their limited grunt-based proto-language, their children were experiencing this new 10-year developmental window.
Okay.
They were playing together in the dirt with unpruned hyperplastic brains. And as they played, they invented cryptophagia secret languages.
Wait, we actually see this today, don't we?
We do.
Modern twins will sometimes develop an intricate babbling language that only they can understand before they fully adopt the language of their parents.
Exactly. And in this prehistoric setting, these children weren't just babbling. They made a specific linguistic breakthrough that fundamentally changed the math of human existence. They invented spatial preposition.
Prepositions, like behind.
Yes. Words that define relationships like behind, under, next to, or inside.
Let's actually do the math on that because the sheer scale of what a preposition unlocks is staggering.
It really is.
Let's say your primitive tribe has spent generations building a vocabulary of 1,000 words. Just nouns and verbs. Rock, tree, run, bear. With 1,000 words, you can describe exactly 1,000 distinct images. It's a strict 1-to-1 ratio of word to reality.
The communication ceiling is very low.
Right. But the moment those kids playing in the dirt invent just one preposition, let's say they invent the concept of behind the ceiling shatters.
Completely shatter.
Because now you don't just point and say rock or tree, you can say the rock behind the tree. You have linked two separate concepts in physical space.
Yeah.
By adding one single preposition to a 1,000-word vocabulary, your communication potential jumps from 1,000 distinct images to 1,000,000 possible combinations.
It's the exponential power of syntax.
And if you add just 3 more prepositions, bringing your total to 4, your ability to describe distinct, unique images skyrockets to 27 trillion possibilities.
It's mind-boggling.
27 trillion. Just from children playing around with spatial relationships and figuring out how things connect.
And this mathematical explosion is what gave us mental synthesis. It is the defining human superpower.
Mental synthesis.
Yes, mental synthesis is the ability to construct a complex, multi-layered image in your own mind and code it into acoustic data using your vocal cords and copy that exact image perfectly into someone else's mind.
So you synthesize an image that doesn't exist anywhere except in your brain and you transmit it.
Exactly. And once our ancestors unlocked mental synthesis, the physical world was entirely at their mercy. You look at the archaeological evidence from roughly this era, like the desert kites found in the Negev desert.
Oh, right. Those massive traps.
Yes, those structures are a perfect physical manifestation of mental synthesis. Desert kites are massive, V-shaped stone walls, some stretching across the landscape for 60 kilometers, designed to funnel wild game into a specific kill zone.
Which is incredible because you simply cannot coordinate hundreds of people to build a 60-kilometer trap over hills and valleys using just grunts and pointing.
No, absolutely not.
You have to be able to describe a blueprint of something that doesn't physically exist yet. You have to be able to look at an empty desert and say to your tribe, the wall needs to start behind that ridge, run next to the dry riverbed, and end under the cliff.
You are actively architecting reality through language. It wasn't that our muscles got stronger or that we suddenly invented sharper spears. It was our newfound ability to share a hallucination of the future and then coordinate our actions to build it.
That is just, wow. So tracing this entire journey back, every text message you send, every complex joke you tell, every novel you've ever gotten lost in,
Yes.
it is all the result of a spectacular, cascading evolutionary storm.
Yes.
It started with the daily choking hazard of a lowered larynx acting as an acoustic guitar. It relied on a microscopic two-amino acid shift in the FOXP2 gene that bypassed our emotional triggers and gave us precise motor control.
And the regulatory genes.
Right, regulatory genes building broadband neural fiber optics. And finally, it required the chaotic, unpruned brains of vulnerable children, playing in the dirt, to invent the mathematical rules of syntax that unlocked 27 trillion possibilities.
It was the perfect, fragile synthesis of a dangerous biological gamble and a cultural spark. And the vehicle that allowed that spark to catch fire was the long, slow, completely unstructured human childhood.
Yeah.
Which honestly brings us to an incredibly unsettling question about where we are heading next.
Where does this evolutionary trajectory take us now?
Think about the environment that created mental synthesis. It required delayed brain maturation, a long, slow developer mode, interacting deeply with the physical world, figuring out spatial relationships from scratch.
Right.
But in our modern world, children's crucial neural pruning phases are experiencing an environment that has never existed before. That precious 10-year developer mode is constantly interrupted by glowing digital screens, artificial intelligence, and hyper-fast algorithmic video feeds.
The images are being synthesized for them.
Relentlessly. They don't have to construct the purple dog ghost in their mind. The screen generates it instantly. So the question becomes, are we on the verge of a new, unimaginable linguistic and cognitive leap as our brains adapt to processing this endless deluge of external data? Or are we watching the silent biological collapse of our ability to create infinite worlds from within?
Wow. It really makes you wonder if our brains will just rewire themselves over the next few millennia to become passive receivers rather than the architects of reality.
It's a terrifying possibility.
That is a heavy, profound thought to carry with you. Thank you for joining us on this deep dive. We hope you take a moment today to appreciate the sheer mechanical and evolutionary miracle happening in your throat and brain right now.
Absolutely.
The next time you speak, remember, you are wielding 27 trillion possibilities. Make them count.